This is the second lecture of our course on complex and algebraic geometry. Today, we would learn about complex functions and the notion of complex derivative. Let's start. So, previously, we learned about the set of complex numbers. We learned the set of complex numbers essentially is the set that we want to do algebraic geometry with. We introduced this set with definition of a new number, imaginary number I, so that I squared would be equal to -1, right? And we learned that C essentially looks like R2 as a set or as a group, right? That's why we sometimes think about it as a plane called complex plane, right? So this is the real part of Z, which is X, and this is the imaginary axis, which usually is denoted with Y, right? Now, today we like to study functions, F, where the domain and target are C. So F is a function from C to C, right? For instance, let's say F of every complex number Z would be, I don't know, let's say Z squared, just as a definition, as an example. Right. So these are the functions we like to study. The functions where the domain is C or a subset of C and the target is also C. So more generally, we might have a function F where the domain is a subset of C. So let's say U is a subset of C and the target is C. Usually we assume the domain is an open subset. I will explain what that means in a second. So we have the function F. The domain is either the set of complex numbers, C, or some subset of C. So let's say this U, this region, is our domain within C. And our function F has target also C, right? Okay. Now we want to say, what does it mean for F to be complex differentiable? So this is the main concept today. What does it mean to be complex differentiable? Or what is the complex derivative of a function at a point? There are three perspectives, three ways to think about it. One is the limit definition of complex derivative. We actually take that as our main definition. So the main thing we are going to discuss is the notion of complex differentiable function, which I'm going to define today. We are going to learn another equivalent way of thinking about complex differentiable functions. It's called the holomorphic function. So there is a closely related notion called holomorphic. And then there would be a third way to think about holomorphic or complex differentiable functions, and that's called being analytic. So the main point today is to learn these three notions and then also understand why these three things are almost equivalent. So this is like the big picture. We would have three different ways to think about this notion of complex differentiability, right? We are going to define each of these, and then we are trying to show they're equivalent or the same. And this is quite essential in our understanding of complex and algebraic geometry. Okay, let's start. Let's start with the definition of complex differentiability. So let's say we have our function from U, any subset of C, open subset of C, and the target is also C. Let's say Z is a point in U. So being open means here we have C, here we have U. It means it doesn't essentially have the boundary, it's the interior of this domain. It means for any point Z we pick, there exists a small disk around it so that it's completely, so let's say, for example, this disk, it's completely within this domain U, okay? It's an interior point. So let's say Z is such a point in U, we would say F is differentiable or complex differentiable at Z with complex derivative F prime of Z defined using the following limit. So we would say F is differentiable at Z if this limit exists. So if this limit exists, what is this limit? So limit of F of z plus h minus f of z over h when h goes to 0. Okay, this kind of looks like the definition of derivative we learned in calculus for functions from R to R, right? Although it looks the same, it's really different. How is that? The main thing here is that here z is a point in the set of complex numbers. This h, which appears here, is also a complex variable. It can be any complex variable, any sequence of complex numbers going to 0. So for instance, let's zoom in here. We have our set of complex numbers, right? Let's say this is C. We have at this point Z, right? Now, what is Z plus H? So let's say this is H. And therefore, Z plus H would be here. And as H is going to 0, Z plus H would be converging to Z. That's one way that Z plus H can go to Z as H is going to 0. However, we can pick H to be this one, and then Z plus H would be here. And as H is going to 0, Z plus H would be converging to Z from above. Or it might be that H is converging to Z to 0 this way. So Z plus H is going to Z along a weird path, or maybe along this other thing. So the point is that here H can go to 0 along any path in the set of complex numbers, right? So because this limit should exist no matter how H is going to 0, being complex differentiable actually is quite restrictive. And we would see that. We would see there are functions which from our intuition from calculus, you would guess they are differentiable, but in fact, they're not. So this is really, really different compared to differentiability we learned in calculus. So let's call this complex differentiable just to kind of mention this is different. This is being differentiable on the set of complex numbers. Let's look at an example. So let's say f of z is equal to z squared, right? This is the claims that it's complex differentiable at any point z. So this is an example of a complex differentiable function. Suppose I want to prove that. So I should say this limit exists, the limit of f of z plus h minus f of z over h exists when h goes to 0, no matter how h goes to 0, right? So let's try to compute this limit. So limit h goes to 0. What is f of z? It's z squared. What is f of z plus h? It's z plus h squared minus z squared over h, okay? Now let's expand this. So this is equal to the limit of z squared plus 2zh plus h squared minus z squared, right, over h, and h goes to 0, right? So here we can cancel z squared with z squared, so this is equal to the limit of 2zh plus h squared, but I can factor h out. I can write this as h times 2z plus h over h as h goes to 0. So h is converging to 0. It's not equal to the number 0. Therefore, we can cancel h and h in numerator and denominator, right? So this is equal to the limit of 2z plus h over h, and h goes to 0. And as h goes to 0, no matter how it goes to 0, it goes to 0. So this is 0 when we take limit. So this would be equal to 2z. So derivative of z squared is equal to 2z. You kind of expect that, right? With a very similar argument, you can show all polynomials in z are differentiable. So if f of z was any, say, complex number, constant complex number an times z to the n plus up to a1 z plus a naught, that would have been differentiable. And the derivative is what you expect I leave that to you to try that for z to the n rather than z squared, but derivative would be n and z to the n minus 1 plus up to a1, and the derivative of a naught is 0, right? What you would expect. Now, this agrees with your intuition from calculus. Now I'm going to show you an example which does not agree with your intuition from calculus. So here we have f, a map from C to C, right? And any point z in the domain is a complex number, so it can be written as x plus iy for two real numbers, x and y. So as an example, let's say f of z is equal to, well, it's supposed to be another complex number, right? So it has a real part, an imaginary part, right? And the imaginary part is the part which is multiplied by I, right? Let's say the real part is x plus y and the imaginary part is x minus y. Is this function differentiable or not? Is question. Is f complex differentiable or not? Well, if you're not already familiar with this, I'd like you to pause here, think about this for a minute, decide if you think this is complex differentiable or not, and maybe write that in the comments or write it for yourself, and then watch the rest. Okay, so if I want to see if it's complex differentiable or not at any point, I should look at the definition of the limit, right? I should see if this limit exists. If the limit of f of z plus h minus f of z over h, where h goes to 0. We should decide if this limit exists or not, right? So h is a complex number, right? So h itself is a complex variable, not a number, but a complex variable that is going to 0. So it itself has a real part and an imaginary part. So itself is of the form, say, h1 plus, say, h2, where h1 and h2 are a real part of h and imaginary part of h, and they are also going to 0. So if h is going to 0, it means the real part and the imaginary part should also go to 0, okay? Now, why is that important? So what is f of z plus h? So f of z was x plus y plus x minus yi. So z plus h would be x plus h1. This is the x part. Plus y, which would be y plus h2. This would be the real part. Plus I, imaginary part. Was x minus y. Right? This is f of z plus h. So what is the limit we should check? The limit of h goes to 0, f of z plus h, which is x plus h1 plus y plus h2, right? Plus I, x plus h1 minus y minus h2 minus f of z. What was f of z? It was x plus y minus x minus yi, and the whole thing divided by h. So, and h is h1 plus I, h2. Now remember, h going to 0 is the same as h1 and h2 both going to 0. Right. Okay. So here we can cancel x with minus x. We can cancel y with minus y. We can cancel here ix with minus ix. We can cancel minus iy with minus iy here. What remains is the following. So this is the remaining part. So we have the limit h goes to 0, h1 plus I h 1 plus h2 minus IH2. That's what remains from numerator. In the denominator, we have H1 plus IH2, right? Now, as I said, H going to 0 is the same as H1 and H2 going to 0. Does this have a limit? Does this limit exist if H1 and H2 are going to 0? So, you know, H1 and H2 can go to 0 along any path they want. So for instance, let's say this is the set of complex numbers, and this is 0, and H is a complex variable which is going to 0. It can go to 0 along this path, along the real axis. This is called the real axis. It can go to 0 along the imaginary axis. Okay. So what is real axis? Real axis means the imaginary part of H is 0, right? H is equal to H1 plus IH2. So if I assume that H is going to 0 along the real axis, it means H2 is equal to 0, fixed equal to 0, and H1 is going to 0. So it means we are going to 0 here. So this limit should exist if we take the limit along this axis. What would be the value of the limit? So here H2 is equal to 0, so we can just discard H2. So then the numerator would be H1 plus IH1, and the denominator would be just H1. And then if we cancel H1, what remains is I plus 1. That would be the limit. If H goes to 0 along the real axis, what if H goes to 0 along the imaginary axis? Along the imaginary axis, well, there, H1 is equal to 0. On the imaginary axis, there is no real part, so H1 is 0. And H2 is converging to 0. So there, in the limit, we can discard H1. We still have limit here. I'm just a bit lazy, right? So here we have limit. H2 is going to 0. So H1 is 0. We discard H1. The remaining thing is H2 minus IH2. And then in the domain, in the denominator, we have IH2. We can cancel H2 with H2, and the remaining thing would be minus I minus 1. So if the limit exists, it should be a fixed thing. But here, these two numbers are not equal, right? This is a contradiction, which means the limit we started with, it does not exist. If H goes to 0 along two different paths, we get two different answers. That is not possible. So we don't have a limit. That implies the function we had here, this function, x plus y plus x minus yi, this function is not complex differentiable, is not complex differentiable, right? It's a bit weird. From the kind of point of view of calculus, x plus y and x minus y, they're completely smooth, right? They're differentiable. They're very nice functions. But from the point of view of complex numbers, they're not differentiable, okay? So why is that? A general fact which we can prove, and we would probably later, or I might leave it as homework too, is that earlier I mentioned if you have a polynomial like f of z equals z squared, it would be complex differentiable, right? You can write this in terms of x and y, right? Z squared is x plus iy squared. And if you square this, you get x squared minus y squared as the real part plus I times 2xy as imaginary part. So this is f of z. This was differentiable, right? This was differentiable. So happy. But f of z equal to x plus y plus I, x minus y is not differentiable. How is that? So they're both polynomials in x and y. How is that one of them is differentiable and the other one is not? So the essential thing is that this polynomial in x and y can be written as a polynomial in z. And a polynomial is differentiable in the complex sense if and only if you can write it as a polynomial in z. Here we have a polynomial in x and y. If you try to write it as a polynomial in z, you would also see there would be terms in x conjugate, right? You cannot write it as a polynomial. You can try this. You cannot write it as a polynomial just in z without its conjugate. And it's a theorem. A polynomial in x and y is complex differentiable everywhere, if and only if you can translate it to a polynomial which only has terms in z, right? You can think about this why that's the case. Going back to our big picture, I mentioned we have three perspectives to think about complex derivative. One is being complex differentiable in the sense I mentioned, which really means in this complex limit language. There are two other ways. One is what is known as being holomorphic. We would learn this in the next part of this lecture. It's related to a notion called Cauchy-Riemann equations. This is a very useful way to think about these functions. And the third one is the notion of being analytic. This is related to having a kind of power series, a kind of infinite expansion. And the claim is that these three are essentially the same. So at this point, we are here. In the next lecture, we are going to discuss the notion of holomorphic functions and the Cauchy-Riemann equation. Let's finish this part with a question. So this question is for you, and I'd like you to think about it and tell me what you think. So in the definition of complex derivative, we said limit, we should look at this limit f of z plus h minus f of z over h, where h goes to 0. And I mentioned h can be written as h1 plus I h2, right? So h is going to 0. Right, this is 0. H can go to 0 along any path, along any weird path, right? But the question is that, would it be enough if rather than looking at every possible path that H can go to 0, would it be enough if we only look at two of them? If we only consider the path where H goes to 0 along the real axis and the path where H goes to 0 along the imaginary one. If we just check these two, so on one of them, h1 goes to 0 and h2 is equal to 0, the other, h1 is 0 and h2 goes to 0. So if we just check these two, would that be enough? Or do we really need to consider any weird path where h is going to 0 along that path in the set of complex numbers?